Hello, welcome to the benefits of building electrification. Today we'll be talking about the benefits of heat pumps and how to electrify our homes and businesses. My name is Leanne Harvey and I'm a senior building systems consultant with Stephen Winter Associates. From decarbonization to accessibility, we provide research, consulting, and advisory services to improve the built environment. This webinar was developed by Stephen Winter Associates and the City of Denver through the Better Buildings Workforce Accelerator, which was developed to support efforts that raise the level of building science and energy efficiency knowledge in the building-related workforce. This training is geared to HVAC installation contractors, and we'll be talking about electrification in the context of both commercial and residential buildings. By the end of this training, participants should be able to explain the benefits of cold climate technologies for the Denver market, discuss technical solutions to electrify Denver's building stock, showcase the availability of cold climate technologies for the Denver market, and access Denver resources such as training and incentive programs. Today we'll start with some background information on electrification in Denver. We'll talk about the why. Then we'll spend the bulk of our time in the details of how to electrify, and finally we'll highlight some available resources and wrap things up. For our background, we'll look at relevant policies in Denver. Energize Denver was created to implement a building performance policy that includes energy efficiency improvements and strategic electrification of all existing buildings and homes, so they achieve net zero energy by 2040. The Energize Denver Ordinance is broken down into 3 sections: benchmarking, performance, and electrification. To learn more about the ordinance, you can watch existing presentations that are hosted on the Energize Denver Hub. Please visit the QR code seen here. The electrification program, or renewable heating and cooling, is a key aspect of the Energize Denver Ordinance, which focuses on amending the Building and Fire Code and is implemented by community planning and development. The code update requires partial electrification of space and water heat when systems are being replaced. To learn more about this equipment, visit the QR code on the screen. So let's spend some time on the question of why we should electrify, looking at the benefits of electrification and addressing some of the myths that we hear most often from the workforce. In 2019, buildings and homes accounted for 64% of all community-generated emissions, and gas use alone accounts for 24% of Denver's carbon emissions. Replacing gas equipment with efficient equipment powered by renewable energy helps slow down and reduce the worst of climate change impacts such as warmer temperatures and precipitation shifts. Total greenhouse gas emission savings will vary by building type and equipment type, but on average for equipment installed, electrification will result in approximately 20% greenhouse gas savings relative to gas appliances over the equipment lifetime. As we clean the grid, emissions from heating our home will continue to drop. And all electric equipment has the potential to improve the use of the electric grid and inspire new utility incentive mechanisms, where the utility rewards the customer for using energy in a way that reduces the impact on the grid. For example, heat pump water heating already stores heat energy and can be used as a flexible grid asset if coupled with appropriate controls. Electrifying our buildings creates a significant opportunity for increased business for contractors and an influx of good-paying jobs. Currently, natural gas is used to heat the majority of our homes and businesses, accounting for 88% of commercial buildings, 61% of multifamily buildings, and 81% of single-family homes. Gas used for water heating is also high, representing 66% of commercial buildings, 79% of multifamily, and 84% of single-family homes. Given these numbers, there is a lot of work to be done to replace those systems. The amount of replacements needed also presents opportunities to the workforce to gain new skills, grow their businesses, and train up and keep quality installers and contractors. Electrification also creates opportunity to even the playing field and increase comfort for all. Approximately 30% of Denver homes do not have air conditioning, most homes in low-income communities. Neighborhoods with the highest heat risk are the same neighborhoods facing the greatest inequalities. Rising temperatures exacerbate the long litany of public health risks faced by under-resourced communities. With the increase in air pollution from intense and frequent wildfires, traditional methods of cooling homes, like opening windows overnight or using swamp coolers, are no longer healthy options. Electrification through the deployment of heat pumps provides simultaneous heating and cooling, supplying a much-needed quality of life and safety resource. Gas prices are less stable than electric prices over time, so homes and buildings that transition today will achieve more stable utility costs in the long term, as well as cost parity. Getting ahead of the impending electrification transition ensures that those with fewer resources are not left paying more in gas costs to support stranded assets. A successful transition would allow households to transition to renewable heating and cooling, regardless of economic status. And we want to reiterate the job opportunities as an equity benefit as well. An analysis by Inclusive Economics forecasts that building electrification for both space and water heating will result in 600 to over 1,000 jobs in Denver within the next 30 years. And finally, electrification can improve health and safety. We spend most of our lives indoors, and surprisingly, indoor air quality is often worse than the air quality outdoors. Gas appliances create a significant chronic health risk for thousands of climate-vulnerable residents. A recent article in Science Advances indicates that people of color are exposed to greater levels of particulate matter than white households, and residential gas combustion and commercial cooking are among the largest sources of those relative disparities. Residents of homes with gas appliances have nearly 3 times the rate of asthma compared to homes with electric appliances. We see this happening in Denver. A grant-funded weatherization program for income-qualified households found that 30% of these homes' gas appliances failed carbon monoxide safety tests. Heat pumps are a safer option compared to gas or liquid fuels. There is no chimney, gas line, oil tank, or burning of fuels, and no risk of generating carbon monoxide. There are often the same concerns raised when we're talking about how to scale building electrification. We want to help distinguish fact from fiction and address some of the myths that are out there, starting with the myth that electrification isn't common. Electrification is a key strategy for climate policy, and we're seeing initiatives to electrify buildings all over the country. Out of the 44 states and cities that have adopted a benchmarking policy, 10 have advanced their policies from transparency and disclosure to a building performance requirement. The exact requirements vary by municipality. For example, here in Denver, the performance target will be based on site energy use intensity. But in New York, the target is based on greenhouse gas emissions. Regardless of the metric used to set the standard, moving away from on-site fossil fuels and toward ultra-efficient electric systems will be a key strategy for achieving these standards. Not only are other jurisdictions working towards electrification, but the state of Colorado has been laying the groundwork for this transition, starting with the first voter-approved renewable portfolio standard in 2004. Other bills that support electrification include the House bills that set a greenhouse gas reduction goal of 90% by 2050, compared to a 2005 baseline, set energy efficiency standards for new appliances, allows for CPACE financing for housing authorities, and clarifies habitability standards. And there are Senate bills that have established the Air Quality Enterprise Fund and requires the PUC to establish energy savings targets and approve plans for utilities to promote the use of efficient electric equipment. The next myth we'll address is that the technology isn't there yet. We hear a lot of concern about the efficacy of heat pumps because they've had a pretty bad reputation in our region. The original heat pumps that we started seeing in northern climates were really built for use in the South, and they worked well in the South. But they didn't work well when it got cold outside, which kind of set heat pumps back when some early adopters tried to use them up north. But we're not talking about the heat pumps from 10 years ago. The technology has significantly advanced addressing the issues that pumps used to face in colder climates. Cold climate heat pump technology is reliable and is rapidly expanding across the globe. They've been tested and are popular options in northern European countries with harsh winters, and are used domestically in New England and upper Midwest. Below 0 degrees Fahrenheit, cold climate heat pumps can still heat your home with more than twice the efficiency of gas heating or standard electric heating. And they're still dependable even below negative 20 degrees. In summer months, cold climate heat pumps operate as efficiently or more efficiently than brand new air conditioning units. As of 2020, almost 18 million US households use heat pumps for heating in a variety of housing types and are shown to reduce household energy consumption by up to 40%. What about the question of whether or not the grid can handle the electric demand? Denver's electric grid is already built to withstand high air conditioning load during the summer. An analysis found that the grid can support electrified winter heating needs without significant infrastructure build-out. In the near term, Denver should be able to electrify at least 50% of buildings without requiring additional system-level generation and transmission capacity. Electrified equipment will improve the utilization of the current electric grid and could put downward pressure on utility rates while improving the economics of building electrification. In the long term, collaboration on grid stability will be a key part of the planning for a carbon-free future. The exact nature of grid impacts will depend in large part on the types of heat pumps installed in buildings, and grid impacts could be mitigated significantly by building shell improvements and other energy efficiency hybrid heat pumps, as well as high-efficiency cold climate air source heat pumps. What about the question of cost? Under current electricity and gas rates, electrification is cost competitive when replacing existing systems that have reached their end of life. In fact, in Denver, 66% of homes, 69% of multifamily units, and 49% of commercial buildings can be fully electrified while keeping total capital and operating costs within 10% of baseline costs. Since they consume less electricity in moderate weather, heat pumps cost much less to operate on an annual basis compared to legacy systems like combustion furnaces and boilers. Additionally, gas prices will be less stable than electric prices over time. Economy-wide shifts away from fossil fuels assumes likely increases for fuel users. A recent study in California suggests that as gas use declines by 40%, gas prices are likely to start to increase substantially. So homes and buildings that transition in a cost-effective way today will achieve more stable utility costs in the long term, as well as cost parity. Through partial electrification, which is what Denver recommends for most multifamily and commercial buildings, users can make the most of both the gas furnace and the electric heat pumps. The gas can be used as a backup fuel to meet extra demand if needed. In the long run, as emission targets become more stringent, and a mature market and workforce reduce other consumer costs, supplemental gas backup heat can be phased out in favor of fully electric retrofits in all cases. Partial electrification may be more appropriate for buildings with higher heating bills or outdated electric panels, or for customers who are concerned with increased operating costs. Full electrification may be more appropriate for new construction and major retrofits, as well as those who are motivated by carbon reductions, want to leapfrog interim steps, or are looking to pursue electric vehicle charging or on-site solar. Additionally, there are a wide range of incentives, rebates, and financing opportunities that are currently available or will become available soon. Energize Denver has some great programs and pilots, and there are others available through utilities as well as state and local organizations. Soon we'll also begin to see tax rebates and incentives from the federal government through the Inflation Reduction Act. Scan the QR codes to learn more about these opportunities. Now let's dig into the how. We'll review heat pump basics, go over system types, and discuss domestic hot water. So how do heat pumps actually work? Heat pumps do not generate heat, they move it. This means that these systems are extremely efficient because there is no lost energy like we see in a combustion process. Heat pumps can be 200 to 300% efficient. Because they run on electricity, they will also use less carbon-intensive fuel sources as Denver's grid gets cleaner. Finally, even though natural gas is currently less expensive than electricity, heat pumps will still achieve cost parity because they require 2 to 3 times less energy than gas systems. The way heat pumps move heat is by using refrigerants. A refrigerant is a compound typically found in either a fluid or gaseous state within a refrigeration or space conditioning system and can provide heating or air conditioning when combined with other components such as a compressor, condenser, and evaporator. The refrigerant used has a big impact on the operating characteristics of a given heat pump. If you're harvesting heat from the outdoors and pushing it into your building during the winter time, the type of refrigerant that's used can play a role in how well that heat pump works at cold temperatures. The refrigerant used can also have a big impact on the climate. Global warming potential is a measure of the relative global warming effects of different gases. The global warming potential indicates the amount of heat trapped by 1 ton of a gas relative to the amount of heat trapped by 1 ton of CO2 over a specific period. Most hydrochlorofluorocarbons, HCFCs, and hydrofluorocarbons, HFCs, refrigerants have a global warming potential that are thousands of times higher than the potential of CO2. For example, R410A, a common refrigerant used in heat pumps today, has a global warming potential of over 2,000. This means that the emission of 1 ton of R410A will create the same contribution to global warming as the emission of more than 2,000 tons of CO2. This means that to minimize buildings' greenhouse gas emissions, it is important to make sure heat pumps are installed properly, there are no leaks of refrigerants, and the global warming potential of refrigerants is taken into consideration. Next, we will review the different types and configurations of heat pump systems. Let's cover some terminology first. Heat pumps come in a variety of forms. Air source heat pumps take heat from the air and push that heat into another air stream or into water. These are used to move heat in and out of a building. Water source heat pumps take heat from a water source or a water loop, for example, and either discharge it into another water loop or into the air. And ground source heat pumps, which are like water source heat pumps, push and pull heat from the ground via a water loop. We won't be going into much detail on ground source heat pump systems, as they are a less common option for retrofits. First, we will review air source heat pumps. Again, these systems move heat in and out of the building using the air outside of the building. These systems come in both unitized and central configurations. Unitized configurations mean that there is one unit per space. This could mean per room or per apartment. Central configurations mean that there is a central bank of equipment that serve multiple spaces or apartments, and these spaces share common distribution loops. Air source heat pumps come in a variety of configurations and have several different types of indoor units. A key point for all the technologies that we will be presenting is that cold climate systems must be chosen. It is really important to request manufacturer data for your climate and altitude when sizing and selecting units. I'm sure you're very familiar with PTACs, which use electric resistance heat, but packaged terminal heat pumps, or PTHPs, instead provide more efficient heat pump heating. These systems are decentralized and unitized, providing heating and cooling to a single room. And some models provide heat recovery ventilation kits. There are several considerations when it comes to selecting and installing system types. With PTHPs, the refrigerant is contained within units, minimizing the risk of leaks. Again, cold climate models must be chosen, but there are limited options available in the market today. Many models are not designed for high efficiency in cold climates, so backup electric resistance may be needed for particularly cold days. These units also require condensate drains at every unit. PTHPs are a great retrofit option for PTAC buildings, which make up around 2% of Denver's building stock, and it's easy to upgrade for more efficient or lower global warming potential units in the future. Just slide out the PTHP and replace it with a new one. We've seen these utilized successfully at La Tela, Denver's first 100% permanently affordable for-sale condo complex. The project team utilized PTHPs so that each condo owner had more control over temperatures in their units. They also took advantage of mini splits for this feature as well, which we'll dive into next. Mini split heat pumps are also decentralized, a single zone system that provides heating and cooling to one unit. There is one outdoor unit for each indoor unit, and indoor units can be either ducted or ductless. These are typically used for smaller buildings, and they're a good electrification option for much of Denver's building stock with gas furnaces. They tend to be lower cost than other split system options and have a higher coefficient of performance than other split system options. There are many considerations to take into account for mini splits as well. Maintenance is often a concern with decentralized systems due to increased quantity of equipment and accessibility. And because the outdoor and indoor units are one-to-one, outdoor equipment spacing should be taken into account. They need to be hung on an exterior wall, put on balconies, or utilize rooftop or terrace spaces. Using the rooftop will impact size, arrangement of current or future PV systems. Next up is multi-split heat pumps, which are just like mini splits, except they're multi-zoned, meaning you can have 2 or more indoor units per outdoor unit, and each can have separate zone controls. These can also be either ducted or ductless. They're typically used for smaller buildings, being another good retrofit option for much of Denver's building stock, particularly in buildings where separate zone controls may be desired. And the considerations are the same as mini splits. With multi-splits, you have even more indoor equipment, so maintaining these units can be challenging in multifamily buildings. Additionally, the multi-split systems have more refrigerant. Now we'll look at variable refrigerant flow, or VRFs. VRFs differ from the previous system types as they are a central multi-zone system. They can provide heating and cooling to multiple apartment spaces. These are most applicable for commercial and multifamily buildings, or generally taller buildings, as these systems have longer refrigerant line length limits than mini and multi-splits. These systems have modular outdoor units and many different types of indoor units. Some considerations: VRFs require fewer outdoor units, but multiple dwellings or spaces may be affected if the system goes down. They also have more refrigerant volume, so proper installation, pressure testing, and evacuation is critical. VRFs also come with heat recovery. Many manufacturers state that heat recovery models should be used in multifamily settings. Heat recovery systems provide simultaneous heating and cooling to multiple apartments. They are more efficient, offer more control, and can meet thermal needs of different apartments at the same time, so you don't have to decide how to change over mode based on the season. However, thermal zoning must be carefully planned out to realize efficiency potential and to operate as intended. Denver has a great case study using VRF with heat recovery, which is the Boulder Commons project. Boulder Commons is the largest multi-tenant net zero energy project in the U.S. and among the first multi-tenant buildings in the U.S. to achieve net zero energy. VRF with heat recovery was key to reducing their energy load to achieve that designation. Finally, we'll look at another centralized system, rooftop units, or RTUs. Gas heat RTUs make up a big portion of Denver's existing building systems, so this is a major electrification potential in the city. There are many RTU models that exist that include a cold climate heat pump section to meet loads. These models also have energy recovery wheels to help bring down the load passively. Energy recovery involves harvesting waste heat from return or exhaust air to precondition the outdoor air, thereby bringing down the load. If pursuing a partial electrification strategy due to capital costs, it is very important to carefully consider controls, interconnection, and integration. They can get very complicated, so it is important to pay attention to controls. Now that we've looked at the different types, let's review some of the practical retrofit considerations when deciding between centralized and decentralized systems. With decentralized systems, you need to identify the location for many outdoor units. They require more refrigerant and condensate lines, but smaller systems, and the refrigerant lines are soft tubing line sets. With central systems, fewer outdoor units are needed. Everything is consolidated. Refrigerant lines are also consolidated, but this requires greater refrigerant volume. The project work is more invasive and it requires thorough commissioning and oversight. Next, we'll look at a low-temperature hydronic loop heated by air-to-water heat pumps, or AWHPs. In this system, terminal units accept low or moderate temperature ranges, typically above 70 degrees Fahrenheit for cooling and below 110 degrees Fahrenheit for heating. The AWHP adds heat in the winter to keep the loop at 110 and adds heat in the summer if the domestic hot water load is greater than the cooling load. Heat rejection either accomplished by AWHPs or by cooling tower to keep the loop around 85 degrees in the summer. Next, we'll look at low-temperature hydronic loops. These are heated by air-to-water heat pumps, or AWHPs. In this system, terminal units accept low or moderate temperature ranges, typically above 70 degrees Fahrenheit for cooling and below 110 degrees for heating. Heat rejection is accomplished either by AWHPs or by a cooling tower to keep the loop around 85 degrees in the summer. In a low-temperature condenser water loop, spaces are served by hybrid water-cooled air conditioners or water source heat pumps, while the central loop is served by air-to-water heat pumps or water-to-water heat pumps. So why are the temperatures low? Heat pumps have limited operating ranges and efficient ranges. As we reviewed earlier, refrigerant is a big limiter when it comes to generating high temperatures. It's best to assume under 110 degree water produced on the coldest days, and there are limited options for really cold climates like Denver. High efficiency, low load buildings are more likely to blur the lines between heating and cooling season. Simultaneous access to heating and cooling is important. High-temp hydronics does not play well with diverse space needs because there is no way to inject and reject heat into extreme temperature loops. Lastly, when considering partial electrification, there are a few things that buildings can do to become electric ready. Make sure there is enough roof space and structural capacity set aside for outdoor units in the future. Add in electrical capacity where possible. Make sure there is adequate room for plumbing chases. Install shutoff valves at equipment so that isolation and replacement is easy in the future. And select low temperature terminal units and leave futures for air to water heat pump connections. To summarize, these are the main considerations when it comes to heating electrification. Capacity and efficiency are the main drivers of performance, so it is important to consider these points when choosing the appropriate system for the building. Next, we'll dive into domestic hot water electrification. First, let's review some vocabulary. These are the terms that will come up throughout the section: potable, safe, and drinkable water, domestic hot water, potable hot water, water heater or hot water heater, boilers that make non-potable water hot and water heaters make potable water hot, fixtures or sinks, shower heads, faucets, and Legionella is the naturally occurring bacteria that blooms in warm water and causes Legionnaire's disease and Pontiac fever. Like heating, domestic hot water comes in two configurations: decentralized and central. Decentralized systems involve heating water in many locations, each apartment, dorm, bathroom, under each sink, whereas central involves one or more large plant that heat and distribute water for many spaces. Electrifying domestic hot water is a little different and is not as simple as swapping out the boiler for an air-to-water heat pump, and there are challenges. Because domestic hot water loads in buildings are significant, this is a major area of a building's energy usage that needs to be decarbonized. However, it gets very cold in Denver, and central plants need to deliver hot enough water. Heat pumps with traditional refrigerants, like R410A, struggle to produce hot water on cold days. So plant design and sizing require thought. It cannot just be a one-to-one replacement for the boiler. Finally, a robust freeze protection solution is needed for this equipment. These two graphs show the relationship between efficiency and capacity, the hot water produced, with outdoor air temperature. As you can see, as it gets colder, efficiency and capacity drops. The leaving water temperature, or the temperature of water supplied, also drops off as it gets colder. The efficiency and capacity drop due to outdoor air temperature varies for every make and model of heat pump on the market, so it is important to check performance of the system at cold temperatures. Nameplate specs typically only show operation at an outdoor air temperature of 45 degrees Fahrenheit, so request performance in the appropriate climate and altitude from the manufacturer. There are units available that provide good COP and capacity for Denver's design day, but this means wading through many options that do not. Before we dive into the types, let's set up some basic framework around the system types and technologies that we will cover. This table summarizes the heat pump options for domestic hot water. Existing decentralized systems can be electrified using either integrated heat pumps, meaning that the heat is harvested from indoors, or split, meaning that the heat is harvested from the outdoors. Existing centralized systems and single-family homes can be electrified using integrated heat pump water heaters or split air-to-water heat pumps. However, for larger buildings, central systems are best electrified using split systems with storage. This is because they typically need to produce a lot of hot water, which requires a lot of heat that needs to be harvested, which we will review in a few slides. It's best to get that heat from outside or through a hydronic loop as opposed to indoor spaces, which may not have enough heat to harvest to meet the demands of the system. We'll also talk about non-heat pump solutions for specific decentralized applications. First, let's look at technology options for decentralized domestic hot water systems. Heat pump water heaters are a very good electrification solution for 1 to 4 family homes. As previously discussed, integrated systems like this harvest heat from indoor spaces. There are multiple options and products available in the market. These units are not recommended for multifamily applications due to their dense population, which make adequate heat extraction difficult. They also create cold spots when they run, which creates comfort issues in apartments. These units require adequate clearance in a space with enough heat gain to replace what the heat pump extracts to ensure proper operation. So large banks of multiple heat pump water heaters are highly discouraged. They place a big demand for heat in a relatively small space, and the space tends to not be able to recover its temperature, causing freezing issues and poor operations. These units are also very loud, which makes installation in apartments undesirable. An operating unit behind closed doors was measured to have a noise level of 50 decibels. As a point of reference, 35 or less is recommended in high-performance buildings. Another type of unitized technology is split air-to-water heat pumps. This takes heat from the outdoors to heat hot water. Depending on the existing system setup and size, a decentralized split air-to-water heat pump system may be best. This minimizes the heat loss typical in recirculation systems, which is a huge capacity and efficiency loss on the system through the piping and pumping power. Again, it is important to select cold climate appropriate models, and there are limited options available in the market. Generally, cold climate models using CO2 refrigerant are the best option to produce enough hot water. Again, remember to ask for manufacturer's data appropriate for your climate and altitude before selecting or sizing equipment. In certain decentralized applications, other electric domestic hot water solutions are better suited than heat pumps. Point-of-use water heaters are a great solution for non-residential applications, such as a common area bathroom, kitchenettes, and commercial buildings. These small electric heaters are installed near the fixture. Electric resistance heaters are also a good solution for specific applications like tenant fit-out spaces. These solutions reduce the distributional losses that come with a large central system through the piping. These products are lower efficiency than heat pumps and require relatively large electrical capacity, so they are recommended primarily in cases where the usage is very low and the losses from recirculation would make up a substantial portion of the total load if a central system were used. Central systems are typically found in large multifamily buildings. Storage is needed to meet the inherently variable domestic hot water load in the building. Two heat pump options are available for central domestic hot water configurations: air-to-water heat pumps and water-to-water heat pumps. In air-to-water heat pumps, the major limiting factors are outdoor space required and product limitations. It's important to maintain storage tank temperatures greater than 140 degrees Fahrenheit to prevent Legionella growth. This tends to be possible only for models with CO2 refrigerant. But again, there are limited CO2 refrigerant air-to-water heat pumps in the US market. For water-to-water heat pumps, these must be coupled with a hydronic loop, and refrigerant is not as a concern with these systems. There are large-scale outdoor heat pump water heaters available, which are commercial grade for modular engineered solutions, but there are limitations. While these are widely used in Asia and Europe for domestic hot water, there has been little to no market penetration in the US in multifamily buildings. In the US, they are currently only used in commercial and industrial applications. Products available on the market have wide-ranging specs and use cases. Some products can provide high-temperature hot water on a design day, and others cannot. Some products only work in outdoor temperatures, down to 40 degrees Fahrenheit, and others work down to -13 degrees Fahrenheit. Manufacturers can provide details on what temperature hot water and what capacity each model can generate at different outdoor air temperatures, which is necessary for finding a product that meets your design needs. There are also several strategies to improve the overall efficiency of the domestic hot water distribution system, regardless of the electric technology chosen. Efficiently designed hot water delivery systems reduce the amount of time it takes hot water to reach a fixture, saving both water and energy. Approximately 30% of the energy use associated with the hot water delivery system is wasted in distribution losses. Efficient piping layouts will reduce piping by 40%, resulting in lower pumping energy, material costs, and domestic hot water heating costs. Drain water heat recovery systems are designed to capture the heat that is lost from the hot water going down the drain to preheat the cold water that enters your household water heater. There are off-the-shelf solutions with no moving parts for single-family homes and small buildings. Designing plumbing layouts to take advantage of drain heat recovery is smart in smaller buildings. And waste heat recovery through a packaged unit use can be beneficial in larger buildings. Additional accessories like a black water tank may be required. Monitoring water consumption by fixture, dwelling unit, or riser allows for a more nuanced understanding and management of water consumption than the typical whole building meter. This helps balance the equipment cost, accuracy of readings, and effort needed to find the leak. And specifying or replacing fixtures with low-flow fixtures and aerators and WaterSense certified fixtures where applicable helps reduce overall demand. Again, there are several preemptive solutions that should be considered to make a site ready for electrification. Choose storage tanks instead of instantaneous gas-fired plants, which are harder to retrofit to heat pumps. If you do not use tanks now, leave floor space and structural support for them in the future. Ensure the domestic hot water distribution and recirculation system is properly sized, efficiently laid out, and balanced. Factor extra space to house future piping risers and insulation for chases from the boiler room to the outdoor heat pump units. Leave outdoor space and structural capacity for heat pumps. Install isolation valves around equipment to make isolation and removal of specific portions of the system easier during retrofit. And leave enough room in your electrical rooms for additional future electrical panels, switches, disconnects, and more. That covers our current best thinking on all of the system types and considerations when electrifying a building's heating needs. And there is more information available to refer to when thinking through an electrification project. Please continue to take advantage of the Energize Denver Hub, which has an excellent webinar library to help you improve the buildings you own, manage, or occupy. The Hub also offers technical resources by building size, available financing and incentive opportunities, checklists, case studies, and more. And sign up for the Energize Denver newsletter to stay up to date on news, events, and financing opportunities. To conclude, you should now be able to explain the benefits of cold climate technologies for the Denver market, discuss technical solutions to electrify Denver's building stock, showcase the availability of cold climate technologies for the Denver market, and access Denver resources such as training and incentive programs. Thank you again to our partners who help support this presentation. And if you have any questions about this presentation, please contact Electrification at denvergov.org. Thanks for watching.